Problem 10.8 says refrigerant 134A is the working fluid in the ideal vapor compression refrigeration cycle, which is operating at steady state. We are asked to determine the compressor power, refrigeration capacity, and the coefficient of performance. We know the refrigerant enters the compressor at 1.4 bar, negative 12 degrees Celsius, and the condenser pressure is equal to 9 bar. Also, we know the liquid exits the condenser at 32 degrees Celsius, and the mass flow rate of the refrigerant is equal to 7 kilograms per minute. At state 1, at the given pressure, the temperature is greater than the saturated temperature, which means this is superheated. We look in the superheated tables for refrigerant 134A and interpolate at negative 12 degrees Celsius to determine H1 and S1. From process 1 and 2, we know that S1 is equal to S2 and P2 is equal to P3. P3 is given as the condenser pressure at 9 bar. We use the value of pressure 2 at 9 bar to find S2. Once we find S2, we can interpolate to find the enthalpy at state 2. H2 is calculated to be 281.5600312 kilojoules per kilogram. To find H3, we know the liquid exits the condenser at 32 degrees Celsius. For this process, we use H at saturated liquid at state 3, which is equal to 94.39 kilojoules per kilogram. For the throttling process, H3 is also equal to H4, so we can set it equal to 94.39 kilojoules per kilogram. We can now evaluate the compressor power. We use the work of the compressor equal to mass times the enthalpy at state 2 minus the enthalpy at state 1. We see that the mass flow rate is given in kilograms per minute, so we need to be careful to multiply by 1 minute divided by 60 seconds to make sure of correct units. After plugging in known values, we calculate the compressor power to be 4.64 kilowatts. The refrigeration capacity can be computed by setting Qin equal to mass flow rate times enthalpy at state 1 minus state 4. Once again, we have to be careful of the units. These units gives the answer in kilowatts, but the question asks for the refrigeration capacity in tons. We find that 1 kilowatt is equal to 0.284345136 tons. So we now multiply the 17.19 kilowatts times the 0.284345136 tons to get Qin in the units of tons. This equals out to 4.801 tons. Finally, we compute the coefficient of performance. The coefficient of performance is equal to Qin divided by the work of the compressor. The coefficient of performance is 3.7 and is a unitless answer.